Welcome back to the machine learning lecture. My name is Alexander Wojcicki, and in this lecture we will learn about support vector machines and kernels. We start with introducing the general idea behind the support vector machines approach, and we also discuss the so-called hard margin SVM variant. Then we discuss an extension called soft margin SVM, which turns out to be more robust in practice. And finally, we discuss kernels. Let's start by reminding ourselves what a linear classifier is, which we've studied in one of the previous lectures. We can assume for the moment that we are in a binary classification setting, which means that we're trying to classify the inputs into one of two classes. In this case, we're trying to classify the inputs into blue and green, or class +1 and class -1. And what a linear classifier is simply a separating hyperplane. It's a hyperplane which separates the input space into two halves. All of the points which land above the hyperplane are classified as class 1, and all of the points which land below the hyperplane are classified as class -1. So, the question is, how do we specify this hyperplane, which in 2D, by the way, is just a line, right? How do we specify this hyperplane? How do we parameterize it? Well, one way to do this is in so-called Hessian normal form, where we specify two things. We specify the vector W, which is normal, which is perpendicular to the hyperplane, and a bias term B. And then all of the input points for which it holds WT transposed x plus b equals 0, lie exactly on this hyperplane. The way to think about it is that the normal vector, the vector W, tells us about the rotation of the hyperplane. So as we change the W vector, we change the rotation of the hyperplane, and the bias vector moves the hyperplane up and down. And then if we specify these two values, we have specified our hyperplane, which means we have also specified our classifier, because all of the points above it are class 1, and all the points below it are class -1. Right, so this works in 2D, where the hyperplane is a line, works in 3D, where the hyperplane is an actual plane. Now all of the points above are again +1, all the points below are -1. So let's give one example to see how this might look like. So here we're in 2D, we have the features are two-dimensional, which means that the hyperplane is also specified with a normal vector which is two-dimensional. Let's say the vector W here has this particular values, -1 and 1, and then we have a bias term B, which is -2. Let's see what happens if we plug in different values of x now into this expression W transposed x plus b. For example, let's pick this data point. Let's say this is 1 and this is 2. 1, 2, 3. So this data point would be 3, 1. And we plug it into this expression. So let's compute it. W transposed x plus b, in this case, is -3. Plus 1 is -2, the bias is -2, and this is -4. So we've seen that the value evaluates to a negative number. And this is true for all of the points below the hyperplane. This expression will evaluate to a negative number. And furthermore, the more negative this value is, it means we are further away from the hyperplane, so further down. And something similar holds in the other side. So if we plug in now an input x, let's say somewhere over here, this will evaluate as a positive number. And the further we are away from the hyperplane, the more positive this number is. So now with this, we can already define a classifier. We can define a decision rule. Simply take the sign of this expression. If the sign is positive, then we know we belong to class 1. And if the sign of this expression is negative, we know we belong to class -1. And this is exactly how we define our linear classifier. Now, suppose we're given some training data and we're trying to learn a good classifier. In our case, this means that we're trying to find a hyperplane which does a good job at separating the two classes. If we look at the hyperplane shown on the slides, this one, we see that all of the examples that belong to the blue class are above the hyperplane, and all of the examples that belong to the green class are below the hyperplane. Which means this classifier perfectly classifies all of the training data, means the hyperplane perfectly separates the two classes. And in general, whenever we have a data which is linearly separable, we are always guaranteed to find at least one hyperplane which can perfectly separate the two classes. In this case, if you look at the example, there's more than one. This one also perfectly separates the two classes. This one as well. All of the x's are above and all of the circles are below. Actually, in this case, there's even infinitely many different hyperplanes, all of which can perfectly separate the training data. So then the question becomes, out of all of these hyperplanes, which one do we choose? Which one is a better choice in the sense that it will give us better performance on future unseen test data? And the main idea behind support vector machines is that we should choose the hyperplane which has the largest possible margin. Let's see exactly what this means. If we consider the hyperplane shown on the slides, this one, the first thing we look at is the closest data points to the hyperplane on either side. So the closest circle is this one to the hyperplane, and the closest two x's to the hyperplane are these two. Then we simply measure these distances to the closest data points. So we measure this distance, and we measure this distance, and the sum of these two distances basically gives us the margin. Or in other words, the width of this rectangle is exactly what we would call the margin. In simple words, the margin is the size of the gap between the two classes. Another way to think about it is that if you have a hyperplane, you can imagine a rectangle which is expanding around the hyperplane until you hit a data point on either side, and then you stop. And then the width of this rectangle is exactly the margin. Let's look at a different example. Maybe we have, let's say, this particular hyperplane. And then again, we look for the distance to the closest data points, which would be these two. In this case, for this hyperplane, the margin is this one, which happens to be much smaller than this particular margin. So now we have two classifiers with different margins. Which one should we prefer? Well, let's see what happens if we're trying to classify a new data point. Let's say the new data point is somewhere here. Using the old classifier, this one, we would classify the data point as blue because it's above the hyperplane. But using this new hyperplane, this data point will be classified as green because it's below the hyperplane. But looking at this picture, intuitively you would say that this new dot, the black dot, should be classified as blue because it's closer to other data points which belong to the blue class. And in general, it is true that hyperplanes which have a larger margin tend to lead to predictions which are better on unseen test data. And this intuition can even be made more rigorous, coming based on some results from statistical learning theory back from 1995. Basically, the idea is that classifiers which have large margin can be shown that with high probability lead to low generalization error, which means to small number of misclassifications on future data. And the connection between the margin and the generalization error is made via something called the VC dimension of the classifier, which measures the complexity of the classifier. But these are really not that important details. The whole point is that the intuition that hyperplanes with large margin, if we have a large gap between the classes, lead to better performance, can be made theoretically and mathematically rigorous. Okay, so how do we actually compute this value? How do we compute the size of the margin? Well, the first thing we do is we start with our hyperplane, and then we form two other hyperplanes which are parallel to it. Remember that the bias term simply moves the hyperplane up and down. So then if we add an offset to the bias here with minus s and plus s, we will directly obtain these two hyperplanes which are parallel to the one that we start with. Now, if in addition to this we require that all examples which belong to class 1 are above the blue hyperplane, and all of the examples which belong to class -1 are below the hyperplane, by construction we get that there are no examples in between these two hyperplanes, which means that the distance between them is exactly the size of the margin. So the next thing we have to do is basically compute the distance from the blue to the green hyperplane. The way we do this is by using the formula for computing the distance from a hyperplane to the origin, which is this one. What is happening basically is we're computing the distance from the hyperplane to this line which crosses through the origin. And you can look this up, but the formula is given basically by this expression. Now we plug in this formula for the blue line and compute this distance. We then plug in the formula for the green hyperplane and obtain this distance. And then the difference between these two gives us exactly what we're looking for, which is the size of the margin. Now, if you plug in and work through the numbers, basically the margin ends up being 2 times s divided by the norm of w, where s is this offset parameter which we introduced. Turns out that this offset parameter actually is redundant, and we can simply set it to, for example, 1 without loss of generality. And intuitively, the reason for this is because the hyperplane is only determined by the direction of the vector w. If you scale up w by 10 or scale it down by 2, it doesn't really matter. The hyperplane will still stay the same. You just have to appropriately scale s. But because of this, we can simply set s equals to 1. And if we do this, we get the final formula for the margin, which is 2 divided by the norm of the vector w. Here, as a side remark, be careful, we cannot set the bias term to some arbitrary number, because this will link the distance to the margin. Imagine, for example, if we set the bias equal to 0, then the hyperplane will be the one crossing the origin, which is not what we want. Okay, so now we have the formula for our margin. And basically what we're trying to do is we're trying to find vectors w and b. So we're trying to find the vector w and the scalar b, such that the margin, which is 2 divided by norm of w, is maximized. But we cannot choose just any w and any b. Remember, in order for this to actually be a margin, it has to hold that all of the blue examples are above the blue hyperplane and all of the green examples are below the green hyperplane. Only then does this number measure the margin, which means that we have to enforce additional constraints to make sure that this is satisfied. So where do these constraints come from? If we look at this particular line, we can slightly rewrite it as w transpose x plus b equals 1, because we've basically moved the 1 on the other side. And the 1 below we can also slightly rewrite as w transpose x plus b equals now minus 1, because we moved the plus 1 to the other side. Now, if we want to require that all of these are below, then basically it means that the expression has to be less than minus 1 for all examples which belong to class minus 1. And then for all examples which belong to class plus 1, we have to be larger than 1, because then we're above this hyperplane. Here we can do one small trick where we multiply these expressions with yi. So let's see, if yi is plus 1, then here we just multiply by plus 1, nothing changes, we get exactly this constraint. If yi is minus 1, then this greater or equal flips to less or equal, and this 1 flips to minus 1, which means we get this constraint. So basically we can condense these two constraints into a single constraint by multiplying with yi. So now we're almost there. Basically we want to solve this optimization problem, but subject to these constraints for all I. And this is exactly what we do in support vector machines. We're maximizing the margin, but remember, because the margin is 2 over w, we can equivalently just minimize the norm of the vector w. This is slightly easier to work with, so that's why we specify it like that. And specifically, even instead of minimizing the norm of w, we minimize the norm of w squared. because essentially the square root is a monotonic function and doesn't change the location of the optimum. And we can do this because it makes it slightly easier to work with. So putting everything together, we have an optimization problem in which we're looking for a weight vector W and a bias term B such that the norm of the weight vector is minimized, which corresponds to maximizing the margin, and the constraints, which correspond to, which enforce that all of the data points are correctly classified, are satisfied. Maybe at this moment, what you can do is you can pause and think about what happens if the dataset is not linearly separable. What happens if we cannot find a hyperplane which perfectly separates the two classes? Can we solve then this optimization problem, or would we run into some issues? But looking at this optimization problem, we can see that this is a convex optimization problem, a constrained convex optimization problem, because the objective is a convex function and the constraints are also convex, or in this case, they are even linear. And in general, we have tools, we know how to solve such convex optimization problems very efficiently. Now, before we continue with how we do this in the case of SVMs, we're gonna set aside some time to talk about how we solve these kinds of problems in general. Let's start with some notation. We have a constraint optimization problem. We have the objective function, which we denote with f0. So this is a function which maps some d-dimensional vector of parameters theta to a real value. And in addition to this objective function, we also have a bunch of other functions, fi, in this case m such functions, which enforce additional constraints on our parameter. So just to really make it clear again, this theta in the cases of SVM is the weight vector W and the scalar B. And just to introduce some terminology here, we will call a point theta feasible if it satisfies all of these constraints. Now, when we're solving this optimization problem, the final value, the minimum value of f of 0 of theta, we will call p star, and the point and where this minimum is obtained is called minimizer, and we denote this point with theta star. So basically, p star is f of 0 of theta star. Let me show you one example to illustrate what is happening here. So let's say we imagine that we have some two parameters, theta 1 and theta 2, and the function that we're optimizing is f0, which let's say is theta 1 plus theta 2. And if we do not have any additional constraints and we want to minimize f0, basically the solution is minus infinity, because we can always go lower and lower and get a smaller and smaller value. Now, let's say in addition to these objective function, we have a constraint which says, let's try this constraint, fi or f1, which is theta 1 squared plus theta 2 squared minus 1. And what we're trying to enforce is this fi is smaller than 0, so we're trying to enforce that this value is smaller than 0. And geometrically, this means that we're trying to enforce that the parameters theta live inside the unit circle. Okay, so now if we're trying to minimize the function f0 subject to this constraint f1, all of the points which lie outside of this unit circle are not feasible, which means they're not a valid solution, and we only have to look at the points inside the unit circle, or only the points that satisfy the constraint. And then looking at the point that satisfy the constraint, the point that has the smallest objective value, or in this example, the smallest value of theta 1 plus theta 2, will be a point somewhere over here, and this will be our theta 1, theta 2 star. And the value of f of 0 at this point will be p star. In general, we can have more than one constraint, so additional constraints except this one where we have to be inside the unit circle. For example, maybe an additional constraint would be that the parameters have to be inside this blue rectangle. Maybe a third constraint could be that all of the parameters have to be above this green line, so this would be a linear constraint. And as long as all of these constraints are convex or linear, we know how to solve this problem efficiently. So now basically the parameters have to satisfy that they're both inside the circle and inside the rectangle and above the green line. So if you look at this, the only feasible region which satisfies all of these constraints is within this part. So all of the points that live inside this region are feasible because they satisfy all of these three constraints. And then in this case, the minimum point would be somewhere over here. A general method for solving these kinds of optimization problem is the method of Lagrangian multipliers. Let's start with some definition. We take our optimization problem in which we have the objective function f0 and a bunch of other functions fi which are part of the constraints. And the simple thing we do is we simply add them up with some additional scalars. So we take the objective function and we add all of the other functions part of the constraints, multiply it with some scalar alpha I. These scalars are called Lagrangian multipliers and they have to be non-negative. And this whole function together, which is now a function of the original parameters theta and these multipliers alpha, is called the Lagrangian. So simply we've just created a new function by adding up the original objective function and all the functions in the constraints. Now, the next thing we do is we define the so-called Lagrangian dual function. And this is simply a minimization of this Lagrangian function over all possible values of theta. So we took this new Lagrangian function and we minimize over all possible theta. The resulting thing is a function of alpha, which we call the Lagrange dual function. Here note that theta is completely unconstrained. So unlike before, where we had constraints on which values the theta can take, in the Lagrangian dual, theta is completely unconstrained. And one thing we have to note here, which will help us later on, and is that this function, g of alpha, is a concave function because it's a pointwise minimum of a family of affine functions. So the way to think about it is if you plug in any value of theta as a function of alpha, this is simply a scalar times another scalar plus another scalar. And this holds for any theta, and then if you just take the minimum of all of these, you get a concave function. Okay, so let's see how can we interpret this Lagrangian dual function. Why does it make sense to do such a thing? Well, the one thing that holds, which we'll show here, is that for any choice of alpha, as long as they are non-negative, the corresponding g of alpha is a lower bound on the optimal value of the original constraint problem. So if you imagine the number line, and maybe the value of p star, so the optimal value of the constraint optimization problem is here, which corresponds to f of 0 of theta star. What holds is that for any value of alpha, really any alpha that you plug in, we always get a value which is below this. We always get something which is a lower bound. Let's see why this holds true. We start with the original optimization problem over here. So again, we're looking for a theta such that f of 0 of theta is minimized and all of the fi's are smaller than 0. If we plug in now the optimal value theta star, first it has to hold that this is a feasible point, as we discussed earlier. It has to hold that all of these constraints are satisfied. This means that the value of fi of theta star is always less or equal than 0, because otherwise it wouldn't be a feasible point and it wouldn't be the solution to our problem. And the values of alpha I are by definition non-negative. So if we multiply a non-negative value with something which is non-positive, we together get a non-positive number. So basically this whole sum is less than equal to 0, because we multiply something which is greater than 0 with something which is smaller than 0, which gives us something which is smaller than 0, and if we sum those up, we get something which is smaller than 0. So then at least we know that if 0 of theta star plus this term has to be smaller, because we're adding a smaller number, than f of 0 of theta star. So we know already that this value is a lower bound on p star. Now, if in addition to this we allow theta to now vary completely freely, instead of just using the particular theta star here, if we just minimize now theta, this value can only get smaller. And this was exactly the definition of our Lagrangian dual function g of alpha. So we noted this also on the previous slide. Note that the value of g of alpha can also be potentially minus infinity. So there could be some g of alpha down below for some other alpha where we get minus infinity. Right, so what we've seen from here is that for each alpha which is positive, the Lagrangian dual function always gives us a lower bound on the optimal value p star of the original optimization problem. So then the question is, which alpha do you choose? Well, we simply choose the best alpha. We try to find the maximum possible g of alpha. Again, if you think about the number line, and here is p star, maybe g of some alpha is here, maybe for a different alpha we get g of alpha here, maybe for a different alpha we get g of alpha here, and simply out of all of these we choose the one which is the highest, which is the closest to this p star. And if we denote the value of this new problem, which is now called the Lagrange dual problem, where we're maximizing over this function g of alpha, subject to the constraint that alphas are positive, then what we get out of it is the best possible lower bound on p star. Here, as a side note, we basically try to also enforce an additional constraint that g of alpha is not infinity, because this case is really not interesting. But this is just a minor technicality. Because as we discussed that for any value of alpha, g of alpha is always less than the solution to the original primal problem p star, then also the maximum value of g of alpha, which we denoted with d star, has to be smaller than p star. And this effect is called weak duality, and it always holds. The difference between these two, p star minus d star, basically how far away we are from p star, is called the duality gap. And under certain conditions, we can actually show that duality gap is 0, which means that d star equals to p star. Which means it doesn't matter which problem we solve. We can solve either the primal problem or the dual problem, but we basically get the same solution in both cases. In other words, the maximum of the Lagrangian dual problem is the same as the minimum of the original primal optimization problem. And it holds that f of 0 of theta star equals g of alpha star. This is good news, because now instead of solving the original primal problem, where we had these complicated constraints, fi of theta star less than equal to 0, where fi can be any convex function, now we have a simple constraints which are just that alpha is bigger than 0. And if strong duality holds, the solution to both of these problems is the same, so we might as well just solve the dual problem, which seems like the easier thing to do. Let's see how we can apply now this recipe for solving constraint optimization problems to the problem which was associated with the support vector machines. First, let's recall what was the actual problem that we wanted to solve. We wanted to maximize the margin, which corresponds to minimizing the norm of the vector W. So we want to minimize the norm of W, which we can write as W transpose W, subject to the constraints that all of the points are correctly classified. And those constraints were written as yi times W transpose xi plus b minus 1 should be greater and equal to 0. And this should hold for all I. So now basically these functions are our constraints fi, which we had in the discussion of the Lagrangian method. What we do is, as the method suggests, we take this fi and we multiply them with scalars alpha I and add them to the original objective function, which in this case is W transpose W. So just one more time, these are our fi. One thing I want to point out here is that in the discussion of the Lagrange method, we assume that all constraints are of the form fi less than equal to 0. But in the definition of the SVM problem, we had this fi bigger than equal to 0. So the simple solution is to multiply this by minus 1, which will flip the sign, and this results in this minus which appears here. Okay, so we've defined our Lagrangian, which is now a function of the parameters theta. So these were the parameters theta and the Lagrange multipliers alpha. And the next step was to form the Lagrangian dual function, g of alpha, which is simply the minimum of the Lagrangian function with respect to the parameters, so with respect to w and b. And in this case, this is like an unconstrained optimization problem, so we are free to choose any value of w and b. And we know how to solve this. We simply take the gradient with respect to these parameters, set it to 0, and solve. So let's do exactly that. Let's take the gradient of this function with respect to w. We have two terms. The gradient of this quadratic is simply w, or 2 times w, and then the 2 cancels with 1 half. And the gradient of this linear function is simply alpha I, yi, xi. We can do the same thing for the other parameter, for the scalar b, take the gradient with respect to b, and we obtain this expression over here. Now, solving these equations, we obtain the solution for w and b, which we can then plug in back into the Lagrangian and obtain our dual function. So if we solve the equation, let's say, with respect to w, we directly see that the w is a linear combination of the training samples. And now we can take this w, plug it into here, and then we just get a function of alpha. So here and here. So doing that, we obtain the following Lagrangian dual function, which if you see now is just a function of alpha, and of course the data, xi and yi, and it has these constraints which say that the Lagrange multipliers are non-negative, and this one additional constraint which comes from the gradient with respect to b. But basically now we have our dual problem, and if you remember, the value of g of alpha will give us a lower bound on the prime of problem for any value of alpha. And what we wanted to do is find the maximum lower bound or the best possible lower bound. So that's what we do. We maximize now g of alpha. In general, we can rewrite these kinds of optimization problems into a vector form. And we can basically specify a matrix called here Q, this matrix will depend on the xi and yi from our data set. And if this matrix is symmetric, negative, semi-definite, and we have a maximization problem, then we can solve this problem efficiently. Or the other way around, if the matrix is symmetric positive semi-definite and we have a minimization problem, again, similarly, we can solve this problem, this kind of problem efficiently. And in general, these are called quadratic programming problems, and we have the tools to solve them. And there exist efficient algorithms such as the sequential minimization optimization algorithm, which you don't really have to know. But in the case of SVM, there are even specialized implementations of these kinds of algorithms, and they are widely used in practice and scale to millions of data points. You can find them online and directly use them. In other words, as long as you can write your problem in this form, as long as you can specify this matrix Q, you can call a specialized quadratic programming solver and you'll get the optimal alpha directly. So let's say we've done this, that we've specified the dual problem, called our QP solver, and obtained the optimal alpha star. Now the question is, how can we get the classifier, meaning how can we get the value of the weight vector and the bias, which will give us the hyperplane, which corresponds to this optimal alpha star. For the weight vector, it's pretty easy because, as we've said before, the weight vector is a linear combination of the training samples, and simply plugging in now alpha I star, we directly get the weight vector. For the bias, we need to do a little bit more work. And basically, we have to take advantage of something which is called the complementary slackness condition, which holds whenever strong duality holds. And in the case of the support vector machine optimization problem, this is indeed the case. So let's see how this works. We know that if strong duality holds, then there is no duality gap, or duality gap is 0. Or in other words, D star equals P star. So the solution to the primal is the same as the solution to the dual. Put differently, G of alpha star equals F0 of theta star, where theta star are the optimal parameters, or in our case W and B, which correspond to the optimal alpha star. But by the way we defined the Lagrangian dual G of alpha, we also know that it has to hold that F of 0 of theta star plus sum over all I alpha I Fi of theta star has to equal F of 0 of theta star. And because this term appears on both sides, the only way this is true is if this entire sum equals to 0. In other words, every one of these terms, alpha I, Fi, theta star, has to equal to 0 in order for the entire term to be equal to 0 and strong duality to hold. And this fact is called the complementary slackness condition, which we've written down here. There are actually a set of other conditions called the Kkt conditions, which have to hold for these kinds of optimization problems, which we can leverage, but we're not going to discuss them in more details. Okay, so going back, we know now we know because of this discussion over here that this condition has to hold, and basically we can the only way that this product is 0 is if either alpha I is 0, or this is 0, or both of them are 0. Now, in order to find the bias, we just have to pick some of these terms where alpha I is non-zero, because then Fi of theta star has to be 0. So if we choose Fi of theta star to be 0, by plugging in the definition for Fi in the case of SVM, we get that W transposed Xi plus B Yi minus 1 equals to 0. We can move this minus 1 to the other side and then divide by yi, in which case we get exactly this term over here. From here, solving for b, we get exactly the value that we were looking for. Here, of course, we have alpha I star. In general, these Kkt conditions only hold for the alpha star and theta star, including the complementary slackness conditions, not for any arbitrary alpha and theta. So you should keep that in mind. Okay, so now we've recovered our W and B, which means we have our classifier. Another interesting thing which actually comes out of this complementary slackness condition is that only those alpha I which are non-negative are contributing to our weight vector. So if you think about it, out of all of these alpha i's here, some of them are 0 and some of them are positive, and only those which are positive will contribute a term into this sum. So alternatively, we can write this as sum over some set S, alpha I, yi, xi, where S is the set of alphas which are positive. And from the discussion before, if the alpha is positive, then this term over here has to be equal to 0. And what is this term? So these are those data points which exactly lie on the margin. So if you look at this line here, and you look at this line, so these two hyperplanes, it holds W transposed xi plus b equals -1, and here W transposed xi plus b equals 1, which is what follows from here. So W transposed xi plus b equals 1, and then if you multiply by yi, you either get 1 or -1. So basically only those data points which lie exactly on the margin, which are exactly on these two parallel hyperplanes, will contribute anything to the weight vector, because exactly the alpha i's which are corresponding to these data points will be non-negative, and they will contribute something to this sum. And this is where the name comes from, because these data points are exactly called the support vectors, because the hyperplane is supported on them. One more time, for the support vectors, it holds that alpha I is bigger than 0, the same here and here. But for any of the other input points, alpha I is necessarily 0. And this comes from the complementary slackness condition. So for all of these other data points, alpha I is 0, and only for the support vectors, alpha I is non-zero. So what is one thing that's interesting that comes out of it is, let's say now we have a new data set and we have this additional data points, maybe here a couple of more additional data points. In this case, the solution would have not changed, because none of these additional data points will contribute to the support vectors, or will not be support vectors, or in other words, will not contribute to the final weight vector. What we can also see in this image is that the solution is sparse. There are only very few, in this case only these three inputs which have a non-negative, which have a positive alpha I, which means that we only have 3 support vectors out of all of these possible data points. And having sparse solutions is good because it leads, it's more efficient essentially. Okay, so let's just recap what we've done, everything together. We wanted to construct a linear classifier by specifying a hyperplane. All of the data points which lie above the hyperplane are classified as class 1, and all of the data points which lie below the hyperplane are classified as class -1. And then of all the possible hyperplanes we can choose, we opted to choose the one with the highest possible margin, and turns out that maximizing the margin is equivalent to minimizing the norm of the vector w, which is perpendicular to the hyperplane. And in order to solve this, we formulate it as a constraint optimization problem. In the final solution, we figured out that only those examples which lie exactly on the margin, which are called support vectors, will contribute anything to this weight vector w. So then, in order to classify, we only need to remember these few support vectors, compute the value of w, plug it into our definition of the classifier w transpose x plus b, and simply take the sign in order to predict new incoming data points.